Okay, good. So welcome back after the short break. So now we are, from applications, we are going back to the core theory of parameterized complexity. So now the next two lectures will be devoted to lower bounds for kernelization. So this is a framework to show that some problems, some parameterized problems, probably do not have polynomial kernels. And in the morning, you've seen various techniques to actually get polynomial kernels for other problems. So just to recap, in the kernelization framework, this is a framework within parameterized complexity, we have a big instance of our initial problem L, say parameterized problem, that we want to solve somehow. The problem is probably NP hard, so we don't expect to do it in polynomial time, but at least we can do something. This instance is large, but we expect that maybe it has a small parameter that sort of governs the difficulty of the instance, yes? And now we want to apply preprocessing. In polynomial time, we want to take this instance and turn it into an equivalent instance. So this is a yes instance of our problem L, if and only if this is a yes instance of our problem L. And the size of the new instance should be bounded in terms of some function of the initial parameter, right? So this kernelization. So because we are going to give complexity lower bounds for excluding existence of polynomial kernels, we need to understand what we are doing on the complexity theory level. Yes. So we will be not working mostly with graphs or such things. So we need to put ourselves into complexity theoretical framework. So let me fix some alphabet sigma, say. You can think of it as binary alphabet 0, 1s, yes? That will be used to simply encode the instances that we will be working with. So unparameterized problems, the normal problems in the complexity theoretical setting are just languages over this alphabet, so just subsets of all the finite strings over this alphabet, yes? Which encode the yes instances of our problem that we are working with, yes? In the same way, parameterized problems, yes, they are not just sets of strings encoding yes instances. They are sets of pairs, string encoding the instance, and a single integer that encodes the parameter. Yes, that sort of should govern the difficulty of the instance. Yes. So, given such a parameterized problem, I can always turn it into an unparameterized problem by just appending the parameter in unary after the instance. Yes, so if I have, maybe I can write it down. If I have an instance xk, I can always turn it into one string consisting of x and one put k times. So I append the parameter in unary. Yes? So in this way, every parameterized problem can be made into an unparameterized problem. And the kernelization algorithm in these terms is simply an algorithm that takes a pair xk, this is an instance of my problem L, needs to output an instance x prime k prime, which should be equivalent in the sense that this is a yes instance, belongs to L, if and only this one does. And the total size of the encoding of the output should be bounded by some function of the input parameter, by some computable function. Good. Okay, so we have already seen in the morning this sort of disappointing fact that just kernelization is the same as being FPT. Yeah, so if I have a decidable problem, then having any kernel is equivalent to being fixed parameter tractable. So let me just remind you the reason for this. So if I have a problem that is that has a kernelization algorithm, then it is trivially FPT, yeah? Because I can just compute the kernel and then brute force the kernel, yes? And because I have a decidable problem, I have an algorithm to compute the kernel, and the running time is function of the size of the kernel only, yes? On the other hand, any FPT problem actually has a kernelization algorithm, which is very simple. Let me take the input instance, yes? And let me check, yes, whether the size of the instance is bounded by this f of k governing the running time of the FPT algorithm. If it is smaller, yes, then I already have a kernel of size f of k. Otherwise, this FPT running time is actually polynomial, yes, in the input size. So I can solve the problem in polynomial time and output yes or no. Yes? So this is sort of this encouraging fact for studying just kernels, because the question whether a problem has a kernel is equivalent to being FPT. So we have already the tools FPT versus W1 to classify problems with this respect. What we are interested in here are polynomial kernels, namely kernels whose size is polynomial in the size of the parameter. Yes? And up till 2008, there were scattered sort of polynomial kernels around in the literature, but there was no classification tool to say that this problem shouldn't have a polynomial kernel under some believable assumption. And this technique that appeared in 2008, that by now is sort of in the core of the parameterized complexity, is what I'm going to present to you, and it's called the composition framework. Good. So before I give you the formal definition, let me give you a motivating intuition about this framework. So let's make the following experiment. Let's take the k-path problem. This will be like the most exemplary problem for this talk. So the k-path problem, I've got a graph, say encoded as some string, say binary matrix, yes, and I ask whether it has a path, a simple path on k vertices, yes, whether that does not visit any vertex more than once. Yes, this means simple. Yes, this problem is NP hard because if I put k equal to n, then this is exactly Hamiltonian path, right? I cannot visit any vertex more than twice. So if I ask for going through n vertices, I need to go through all of them. Yes? Okay. So, but we will consider k-path as a parameter problem where k is the parameter. Suppose for a moment that by some magic I've got a kernel for k-path problem that say reduces the input graph, yes, to a kernel with at most say k cube vertices. Yes, this would be a reasonable kernel for this problem. Make the following thought experiment. Take many instances of k-path, say k to 7 of them. Yes, with the same parameter k. Yes. Now take the disjoint union of those graphs. Yes, put them next to each other. Now observe that this graph H has a k-path if and only if at least one of the input graphs has a k-path. Right? Because this k-path needs to be in one of those connected components. Yes? Now, what would happen if I applied my kernelization algorithm to this composed instance? Yes? It will reduce it to some instance with at most k cube vertices. Yes? Which I can encode using k to 6 bits. Right? So which means that I took information from k to 7 instances and I packed them into k to 6 bits. Yes? So the intuition is that in the final instance I needed to lose some information. Yes? So in some sense I needed to lose some information from the input instances, so at least I needed to be able to reason which instances are less prone to have a solution. Yes, to discard them. This is a vague intuition, but sort of explain why this should not be possible. Yes? And because the kernelization algorithm is assumed to do it in polynomial time, this seems unlikely because, well, then this polynomial time algorithm would have some non-trivial insight into an NP-hard problem. Yes? Good. So I hope that this is probably the most important slide of this presentation because it explains why those kernels are actually excluded. Good. So to give you the formal setting, let me start with a few definitions. So first, kernelization versus compression. So in kernelization, I take one instance of my problem L, I preprocess it in polynomial time, I output an instance of the same problem L. So compression is a little bit more relaxed notion. I take an instance of my problem L, parameterized one, with some parameter k. I do some p-time preprocessing or compression, if you want to think about it, and I want to output an equivalent instance of some problem R, maybe that is different than L. Yes? In a sense that this instance have to be a yes instance of R, if and only if this was a yes instance of L. Yes, so this is a like a reduction, sort of, but compressing at the same time. So here the size should be also polynomial, if this is going to be a polynomial time compression, polynomial compression. And by size, I mean here basically bit size. Yes, I will always think about bit size. So this is, of course, a very small difference. Yeah? It's just changing a target problem, but it's also a conceptual difference. Yes. So basically, in compression, if we don't really care what is the target language L, we only care about not mixing yes instances and no instances together. Yes, not mapping them on the same string. Yes, because if I'm allowed to pick any language R as the target one, I could just say the set of all strings that are mapped onto by yes instances, if I do not mix. Yes. So a polynomial kernelization is trivially always a polynomial compression into the same language. Yes. However, if I have a good property, some good properties of this target language L, I can usually turn polynomial compression into polynomial kernelization. For example, if language R is in NP and language L is NP hard, there is a polynomial time algorithm, yes, that reduces R back to L. Yes, and I can pipeline the compression with this reduction. This reduction will yield only a polynomial blow-up because it runs in polynomial time, and therefore this composition will yield me kernelization for the original problem. I just want to remark that there are actually problems where we know a polynomial compression, but we don't know a polynomial kernelization. And these are these weird problems where this target language R into which we compress is not in NP, simply. I will not go more into the details, just a teaser. Good. So now I want to formalize this idea. What does it mean to try to pack information into small space, which should be excluded? And this will be this notion of OR distillation. So far we are working with unparameterized languages, and suppose L and R are two unparameterized languages. So an OR distillation of this language L into the language R is the following algorithm. The algorithm takes on input a big sequence, a large sequence of instances. Think of them as instances of L. Yes? Each of them is quite short. It is of length at most k. Yes? Then I'm allowed to process it in polynomial time, and I need to output one instance y, yes, whose size should be polynomial in this upper bound on the length size, yes, so independent of the number of instances I'm working with, yes, and it should express the OR, the logical OR of the input instances. This should be a yes instance of the target language R, if and only if at least one of those was a yes instance of the input language L, yes. To put it on the picture, I've got many instances of my initial language L, each of small size. I need to process them in polynomial time, and I can output one instance of my language R, yes, that should be small, that should be polynomial in the maximum of the sizes of the input instances, but independent of their number. Yes? So this is an OR distillation, and this should be a yes instance of R, if and only if any of those is a yes instance of L. Good. So the idea here, the intuition here is that you've got this necessary loss of information. Yes, that if you have such an algorithm, then you needed to lose some information about the input, the input strings, right? And if my input language was NP hard, if we were able to do it in polynomial time, yes, this polynomial time algorithm would give some insight into this NP hard problem. Good. So you can also think of this as compression. So let me define for convenience a language OR L. So for any language L, I can define OR L. This is just language of sequences of instances of L, where at least one is a yes instance. Yes, say delimited by hashes. And then OR distillation from L to R is nothing else than a polynomial compression from parameterized OR L, parameterized by the maximum of the input string size, into my language R. Yes? Good. So the main backbone theorem of this whole theory was proved by Fortnow and Santanan in 2008. and it says that this thing is not possible. That the SAT problem, given a propositional formula, is it satisfiable, does not admit an OR distillation algorithm unless bad stuff happens, we usually say, or NP can be solved, is contained in co-NP with polynomial advice. I will explain it a little bit more in a minute. So in particular, this means that no NP-hard problem has any OR distillation unless the same bad stuff happens. Because if any NP-hard problem had an OR distillation, then I could reduce SAT to this my favorite NP-hard problem, yes, and in this manner make an OR distillation for the original problem, yes, by just appending the NP hardness reduction in front of the distillation. Good. So this assumption, for those of you who do not have much background in complexity theory, may seem a little bit mysterious. Let's try to uncrack it. So NP is basically a class of problems for which the proof for having a yes answer is verifiable in polynomial time. Yes? Co-NP, on the other hand, is the class where verifying counterexamples can be done in polynomial time. So verifying proof for an answer no. Yes? So this means NP contained in co-NP would mean that verifying proofs in polynomial time can be turned into verifying counterexamples in polynomial time. Yes? And this polynomial advice, it gives a little bit more power to the machine, to the computation model, but it should not give enough power to actually these things to be contained in each other. So in particular, this assumption implies that the polynomial hierarchy collapses, whatever this means, which is not as severe collapse as P equal to NP, but it is pretty serious, meaning this is considered unlikely. The proof of this theorem is actually super nice, in my opinion. It's one of the gems of complexity theory. You can find it in the book. I will not give it here because this requires understanding more a little bit about what is co-NP, what is polynomial advice, and so on. It would take some time. Let me just give some combinatorial glimpse of what is actually happening in the proof. So the proof is actually showing exactly what we expect, that packing too much information is impossible. And the intuition is that if I have all those sequences, yeah, that need to be packed, that need to be mapped into the small, potentially small set of kernels, then you can actually find a small set of representative kernels. Let me put it in more detail. So suppose you've got this OR distillation for SAT, yes, and I want to solve SAT in co-NP. Yes, with polynomial advice. Don't think about polynomial advice so far. Yes. So what does it mean? This means that given an instance of SAT X, you want to give an NP algorithm, yes, that can do some non-deterministic guesses, yes, but needs to certify that this is not satisfiable. Yes. How do we do this? The idea is that the space of those kernels, yes, is so small, this results of the distillation is so small, that you can sort of find a small set, polynomial size set of sort of representative kernels for all negative instances. In the following more precise sense, whenever you have a no instance, you can sort of hide it in a long sequence of no instances, yes, so that the result of the distillation is one of representative kernels. Yes? So then this list of those representative kernels, because of being of polynomial size, is the actual advice that is given to the algorithm. And this co-NP/poly algorithm for SAT just takes the input instance, guesses this environment in which it will be hidden, yes, kernelizes this via OR distillation, and checks whether this is one of representative kernels. Yes? So this is the actual algorithm. The key is, of course, here to show that the number of representative kernels is small. This is on purpose not giving you all the technical details. This is just the teaser of seeing what is actually happening in the proof. If you want, please look into the book. Good. So, given now this OR distillation theorem, that we know that this OR distillation should be infeasible, we want to turn this into actual proofs that kernelization is implausible. Yes? So let now L be a parameterized language, yes? A parameterized problem. So and our composition is basically like our distillation. It should take a long sequence of instances of my parameterized problem L. It should process them in polynomial time, and it should output one instance of the same problem L, y k star, that behaves like an OR of the input instances. So it should belong to L if and only if any of those input instances was a yes instance, belongs to L. And the target parameter should be polynomial in K. Yeah, because now we are in parameterized complexity, so we measure the difficulty in the parameter. So again, on a picture.
Could you show a difference with OR distillation?
The one difference with OR distillation is that these instances are now parameterized, but the main difference is here. In OR distillation, the output size needed to be polynomial in K. Yes, the maximum of the input sizes. Yes? Here now only the output parameter needs to be small, polynomial. The output instance may be huge. Yes? And the intuition is that such OR composition, together with kernelization, should give OR distillation. Because if you have such a composition, and here you've got only small parameter, you can then apply kernelization to shrink the whole instance size. You will see it in a moment. So let's show it on the picture once more. I've got on input many instances of my parameterized language L. All of them are with the same parameter K. I need to process them in polynomial time and output one possibly very large instance of the same problem L that is equivalent to the OR of those, but whose parameter is bounded polynomially in this input parameter. Yes? And now the intuition is that if now I would make this instance happy by kernelizing it, yes, in total this would give me an OR distillation. Yes? Good. And this is exactly what was proved in 2008 by Bodlander, Downey, Fellows, and Hermelin, that if I have a parameterized problem L that has such an OR composition, and it is also NP-hard in the unparameterized variant, then it doesn't have a polynomial kernel unless bad stuff happens. Yes? So let's do a proof of this theorem, because basically we have already all the tools. Yes? So I will, assuming that there is such a kernelization, and assuming that there is such an OR composition, I will construct an OR distillation for SAT, which, by the result of Fordham-Santanam, shows that this complexity collapse happens. Yes? So I start with many instances of SAT. Yes, so I can think of this as one large instance of OR SAT. Okay, so now my problem of interest, the unparameterized version, is NP-hard. Yes? So I can reduce each of those, yes, to an instance of my language L. Yes? Now each of those, yes, is of polynomial size in the maximum size of the input. Yes? Let me now think of them as actually being parameterized. I mean, these are just encoded in this manner strings. Yes? So I can think of them as actually parameterized instances. They may have various parameters, yes, but all those parameters, because I was putting the parameters in unary, they're all polynomial in the maximum input size. Yes? Good. So let me now group them into groups with the same parameter. And to each of those groups, I apply the OR composition. Yes? So this OR composition composes those instances into one instance that is possibly large, yeah, but has small parameter. Still polynomial in the maximum input size K. Yes? Because all those parameters are polynomial, and this was assumed in the OR composition. Yes? Now, when I have these all instances that are unhappy because they are large, I can make them happy by kernelizing them. Yes? And get polynomially many instances, because there are polynomially many buckets. Yes? Each of polynomial size. Yes? I can put them next to each other and declare them one instance of OR L. Yes? And I have polynomially many of them, each of polynomial size. So this whole instance of our L is of polynomial size. Yes? So in total, this whole chart gives you an OR distillation for SAT. Because if here there was hidden a yes instance, then actually this yes instance would give a path of yes instances here. And if all of those were no instances, then all those instances on this chart would be no instances. Yes? Good. Okay. So let's derive some corollaries of this nice result. So first of all, we can now formally show that K-path does not have a polynomial kernel unless NP is containing co-NP/poly. Why so? Because we have a trivial composition algorithm that I already gave you. Take the input instances, each of them with the same parameter k, just take their disjoint union, and declare it the output instance. Yes? This has a k-path if and only if there was a k-path in at least one of the input instances. Yes? So the same applies to other problems, say k-cycle. I want to check whether there is a cycle of length k in my graph. Yeah? Again, I take the disjoint union of graphs, and it has a k-cycle if and only if one of the input instances had. Yes? So sort of, this opens a bank of results. Yes? Meaning we have a new shiny hammer, and at this point of time in 2008, there was a hammer in our hand, and the nails were everywhere around. Yes? So you just apply it to everywhere. Yes? And by now, basically, investigating polynomial kernelization is the natural next step after showing that the problem is fixed parameter tractable. Yes? And this is the goal to showing that this is the method to show that this is impossible. Okay, so let's add some features to our framework. Okay, so does this proof that we gave actually not only excludes a kernelization into the same language, but actually any compression into any language? Yes? Is it true that if I have an OR composition, yes, of a language into, like, for L, then I exclude even an compression into any language R? I see that some people note. Yes, basically on this chart, yes, if I had here compression, I would end up here with instances of R of polynomial size and declare them one instance of OR R. Right? Good. Okay, so when we start composition, yes, we are mostly interested in this language that we end up with, because this is the language to which we apply kernelization. But do we need to start with the same language, L? Not really. We can start basically with any NP-hard language Q. Yes? Because again on this chart, yes, if here I had an NP-hardest reduction to some language Q, and then I could compose those instances into L, this will be equally good. Good. Okay, so we sort of did this bucket sorting by the parameter size, yes? And we used the fact that we have polynomial number of buckets. Can we do a more refined bucket sorting? Sort of? Yes. Basically, as long as for instances of size polynomial in K, we have polynomial number of buckets. Yes? Because we used this fact at the end. Good. Okay, so now the crucial part. How large this sequence on the input can be, T? Well, in the beginning, arbitrarily large. Yeah? But we can assume that it was at most the total number of strings, yes, of length at most K over the alphabet sigma. Why so? Because if I have more strings, then I have duplicates. Yes? And duplicates, I can just keep one of them because I am only interested in OR of the total thing. Yes? So by pruning the duplicates, I can always assume that the number of instances is at most sigma to power, say, k plus 1. Yes? So we may assume that the logarithm of the number of instances is linear in k. This will be important. So if log t is linear in k, this means that the parameter of the target instance doesn't need to be just polynomial in k. It may be polynomial in k and log t, because log t is anyway bounded linearly in k. Yes? Good. Okay, so what happened after the invention of this technique is that we got a lot of kernelization lower bounds, and a lot of like proofs showing why certain problems, certain classes of problems do not have polynomial kernels. So far we have seen just the disjoint union or composition, but actually like making our compositions is a bit of art, the same way as NP hardness reductions are a bit of art, in a sense that there are many different ways you can do it and many different ideas how to compose things. And often you need to really understand the combinatorics of the problem that you are working with in order to pinpoint the reason why this problem doesn't have a polynomial kernel. Yes? So some examples, some of them were already mentioned here. For example, max leaf. Find a tree with k leaves in a given graph. Set cover parameterized both by the universe size and both by the family size. They do not have polynomial kernels. Steiner tree, if you have seen. Connected vertex cover, where you are looking for a vertex cover that is moreover induces a connected subgraph. All these problems do not admit a polynomial kernel for various reasons. Yeah. And most of these results use some of the features that I have shown, and there was a nice work of Bolan, Rians, and Crush in 2011 that introduced a sort of new framework for doing these compositions called cross-composition framework that sort of aggregates all these ideas that I was mentioning in the previous slide. Yes. So now I will show you this framework because it's very useful. Okay, so first I need to formalize this idea of this bucket sorting. Yes, so the grouping the instances into buckets, into polynomial number of buckets. For this, I need a little bit of abstraction. I will say that an equivalence relation of strings, yes, is a polynomial equivalence relation. Yes. If and only if the following holds. First, I can decide this relation in polynomial time. So given to string, I can decide whether they're equivalent in polynomial time. Second, when I look at instances or strings of length at most n, then the number of equivalence classes among them is at most polynomial in n. Let me give you some examples because this looks magical. Yes? Suppose I've got a graph that is encoded somehow. Yes, say as a matrix. Yes? Then partitioning graphs according to the number of vertices, yes, is a polynomial equivalence relation on their encodings. Yes? Because if I look at strings of length at most n, yes, then I have only polynomial number in n of possible numbers of vertices among such graphs. Yes? Similarly, if I was partitioning graphs according to the number of vertices, to the number of edges, to say the size of the maximum matching, which is polynomial time computable, or the budget of the instance that I am given, if I'm, say, solving vertex cover problem. This is also a polynomial equivalence relation, because in strings of length at most n, the encodings, I will have at most, say, n to the 4 possible equivalence classes. Yes? So this is just refined bucket sorting. Okay, so now I can give you the definition of a cross-composition or cross-composition that formalizes in this language what is a cross-composition. What is a composition? So I have an unparameterized language Q, yes, from which I start, and I've got a parameterized language L. This is the language I am interested in. So a cross-composition from Q to L is an algorithm that takes many instances of Q, yes, a sequence of instances of Q, that I can assume that they're equivalent. Yes, so this is the analog of them having the same parameter. Yes, works in polynomial time, and I would one instance, parameter is one of L, yes, that behaves as an OR of the input instances in the natural way, and moreover, its parameter is bounded polynomially in the maximum of the input size and the logarithm of the number of input instances. Yes, this is just rephrasing in a more robust way of the original concept. Yes, and then we can prove that if I have an NP-hard problem Q and it cross-composes to L, then the latter doesn't have a polynomial compression into n language R unless bad stuff happens. Yes, so let's review the proof again. It will be actually simpler. I start with many instances of Q. Yes. Each of them has size at most k. This is the maximum of the input size. And the number of those instances is at most 2 to the power order of k. Yes? Because I remove the duplicates. I group them according to my polynomial equivalence relation. This I can do because I can compute it in polynomial time. I compose each group separately. Then I compress each group separately. I put them together and declare them one instance of OR. And this yields an OR distillation from Q, which is NP hard, to OR. Yeah? Which is a contradiction with the result of Fortnum and Santanam. Good. So when Bodlander, Janssen, and Crutch came up with this technique, they applied it to so-called structural parameterizations. We will not focus on this during these talks. But in fact, this framework can be applied to basically all kernelization results that I know of. Kernelization lower bound results, of course. And the plan for now, during the remainder of this lecture and during most of the next lecture, is to show you some concrete examples of kernelization lower bounds to show you some tricks, how to prove various things. We have already seen one trick, which is the disjoint union. Yes? But there are many, many more. OK, so the first application I want to talk about, which I think is very nice in the sense that it really distills some concept in kernelization lower bounds, is the set splitting problem. So in this problem, we are given a universe of some elements, a finite universe. And I've got a family of its subsets. Yes? So the input is the same basically as set cover. Yes? A universe and some subsets of this universe. And now I would like to call the parameter for us now will be the size of the universe. Yes? So now I would like to answer whether there's a coloring of the universe into black and white that splits every set in the input. In the sense that every set in the input receives at least one white vertex and at least one black vertex. Yes? I hope that this is clear. Good. So I want to show that this problem doesn't have a polynomial kernel parameterized by the size of the universe, which philosophically means that you cannot reduce the size of this family on input to polynomial in the size of the universe. Yes? So we show a cross composition from set splitting to itself, which in formal terms means we show a cross composition from unparameterized set splitting to parameterized set splitting. Good. So by choosing the appropriate polynomial equivalence relation, we can assume that all the input instances operate on the same universe U, because I can just classify according to the size of the universe, and whenever I have instances on the same size universe, I can just put them on the same universe of this size. Yes? So I'll think that there is one common universe, and all these families are over this universe. We can also assume that T, the number of instances, is a power of 2. This is because I can just take some instances and I can just copy them. Yes? This blows up the number of instances at most twice. T is the number of instances. Yes? So in this cross composition, we are given a sequence of instances. Yes? Instance 1, instance 2, up to instance T. Yes? And I want to output one instance that has small parameter, polynomial in the size of maximum size of the input instance and log T. And it encodes the logical OR of the input instances. Yes? Good. So let me do it. So the input, I hope that this is visible. I will read. So the input are multiple instances on the same universe U. Yes? However, with different families Fi. Yes? F where I goes from 1 to T. And the output should be one instance over some new universe U star with some new family F star. Yes? That I will design in a moment. So first, the new universe will consist of this original universe U, which I will call now playground. Stuff will be happening here. This is why it's playground. And then there is also another part, which I will call instance selector. Yes? And this consists of 1 plus log t pairs of elements. It should be elements, not vertices. Yes? So I put 2 plus 2 log t additional elements to the universe. Yes? They are in pairs, and one pair will be special. Yes? This will become clear in a moment. Okay, so this is the new universe. Observe that the size of the new universe, so the parameter of the target instance, is the size of the initial universe, yes, plus 2 log t plus 2. So this is polynomial in the maximum of the input size and log t. So this is fine. Good. So now I need to design this new family F star so that this new instance of set splitting sort of encodes the logical OR of the input instances. Yes? How do I do it? So first of all, I put into my F star sets consisting of all the pairs. Like, for every pair, I put the 2 elements set consisting of these 2 elements. And note that splitting such a set means that it needs to be colored black-white or white-black. Yes? So there will be like 2 to the log t binary choices. This is crucial. And then for every set x, say originating from some of the input family fi, yes, I create 2 sets in the following way. First, I take this set in the playground, yes, because this set x was actually over this playground, yes, and I append to it like a binary fingerprint of the bit encoding of the instance index on the instance selector. So I take the left special vertex, left special element, plus here, if this set originated in instance fi, yes, I put the binary encoding of the index I. This is one set that I add to my family F star. And the second one is basically the same. I just reverse the stuff on the instance selector. Yes? So basically the idea is that every set originating in the originating in some of the instances is basically preserved. It is exactly the same on the playground. I just append some information to encode from which instance it is originating. Yes? And this additional information is a fingerprint, a binary fingerprint on the instance selector. Good.
On the last row. So the set capital X are the 4 blue dots with circles on the bottom?
No. Yes. This is the set X.
Take 2 new sets from that.
Yes.
Size 4 plus log t.
Plus log t plus 1. Because there are log t plus 1 pairs here. Yes. Okay, so let's analyze it. Suppose I've got some solution to this instance that I found in the end. Yes? So this solution needs to color this instance selector in this way that every pair is either white-black or black-white. Right? So, without loss of generality, I can assume that the special pair is white-black. Why so? Because I can flip white and black. Yes? Meaning these are symmetric. Good. So let's look at this instance selector, and this instance selector now needs to encode in binary some index I. Yeah? So there's, once you think about this, exactly one instance I for which this fingerprint is monochromatic. Yes? All the other fingerprints will be bichromatic. And both of those fingerprints that are appended are monochromatic. So if I now look at this set, for example, that was added as the second one, the fact that all these are black means that in the playground it needs to have a white vertex. And the other one with the white ones, yes, means that it needs to contain a black vertex. Yes? So which means that the instance that is encoded on the instance selector needs to be actually solved on the playground. Yes? So one of the instances needs to be a yes instance. And on the other hand, if one of the instances is a yes instance, I just solve it in the playground and put on the instance selector the binary encoding of its index. And now these sets originating from this instance are already bichromatic because are already split because of what happens on the playground. And all the others are split for free because of the stuff that happens on the instance selector. Yes? They already have a white and a black vertex in the instance selector. Yes? Yes.
Why did we have to symmetrize it?
Sorry?
So for every set we added two sets, x0 star and x1 star. Why both?
Is it only for the second direction? I think yes.
Yes, this is only for the second direction. Yeah.
No, I get it, but just that was a good question.
Good.
Okay, so it's because then if I had a solution, if I didn't do it, would
Yeah, if I didn't do it, yes, I would have like one being fully black or something like this, yes? Here on the instance selector. Meaning I need to have everyone have both a black one and a white one on the instance selector. Yeah.
How do these additional vertices are used?
How these two additional vertices are used? I think the right way to answer this question is to try to omit them and see what goes wrong.
That's why you were here.
Okay. Let me think how to phrase it nicely. So, if I omitted them, then I would have less choices on the instance selector for the actual instances, because the choice white black and the swapping the colors, yes, yields also a solution. Yes? So if I omitted the special guys, yes, I would actually not have possibility of encoding 2 to the log t instances, bit encodings, but 2 to the log t minus 1. Yes? Meaning this special pair is sort of a symmetry breaking in some sense, yeah? It encodes what is considered truth and what is considered false in some sense, or what is considered 0 and what is considered 1 in the binary encoding. Yes? If I omitted it, yes, the binary encoding of an instance and the complement of this binary encoding would be mixed together. Oh, this is the right way to say it. Yes.
Only there for us to agree on what is what.
Yes. Yeah, what is 0 and what is 1. Yes. Yeah. Yes. Good. So to wrap up, the unparameterized variant of set splitting cross-composes into the parameterized by the size of the universe. Unparameterized set splitting is NP-hard. I will not prove it, but I guess you can believe it. And hence set splitting parameterized by the size of U doesn't have a polynomial kernel or even any polynomial compression into any language, yes, unless NP is contained in co-NP with polynomial advice. So the main lesson of this example is the following. So in this example, we sort of modeled the choice of the instance that needed to be solved. Yes? In the k-path example, this was basically very simple because the k-path itself was choosing this instance because it needed to be embedded in only one of them. Yes? Now here we need to sort of prevent mixing of the information from various instances. Yes? And we encoded it in the following way. We added some log t size gadget to model the choice in the combinatorics of the problem of log t bits of the instance that is going to be solved. Yes? And this chosen instance needed to be solved, and all the other were sort of switched off. Yes? This is what morally happened in this proof. Yes? And this idea of this instance selector, so a gadget that chooses one index of the instance to be solved, is an idea that permits many of those kernelization lower bound proofs. Good. Okay, so in the next episode in 10 minutes, I will tell about more proofs. I will talk about end compositions, about weak compositions, which are lower bounds for problems that do have a polynomial kernel to show that they do not have better polynomial kernels. Yes? And finally, I will talk a little bit about string kernelization. Yes, so in 10 minutes, this.